We want to start with a simple question. What if your CI system knew exactly what to test every single time? Like many of you, we felt the pain on waiting on long builds, waiting for CI to build and test targets that we know we didn't even touch. At Tinder, our iOS codebase is about 1.5 million lines of Swift code, with over 300 build targets and more than 40 engineers contributing daily. Our builds used to take up to 42 minutes in CI. That friction added up. It created uncertainty, slow iteration, and left us asking, what if we could make CI smarter? Before we get in too deep, let's first talk about what continuous integration really is. Classical approaches to continuous integration assume nothing. Every build compiles from scratch and runs every single test every time and recreates every artifact. That's because we can't safely skip anything. Now, some teams might layer in optimizations like caching and sharding, but you're still running and testing everything despite these improvements. In the fundamentals, they remain the same. CI doesn't trust partial correctness. 99% isn't good enough. We need 100% confidence, so we pay the price in time. So what if we could change that? As we worked with Bazel, we kept coming back to one simple idea. What if we could just do less work but get the same signal? And it turns out that we can. There's always a smaller subset of build and test targets that give the exact same confidence as building and testing everything. That's the foundation of compute avoidance, a principle that applies whether you're working in a small code base with 10 targets or a large-scale enterprise with tens of thousands. Tools like Bazel Diff make this a general and repeatable regardless of project structure or size. So Bazel gave us caching. It made builds faster, but we're still rebuilding and retesting far more than was necessary. So what we needed was precision, a way for CI to understand context, and that's where Bazel Diff came in. When we began migrating our iOS builds to Bazel, we knew it would bring caching and reproducibility, but even Bazel alone couldn't solve everything. Bazel was still rebuilding and testing far more than it needed to because it couldn't tell which part of the dependency graphs were truly affected by a change. That insight led us to create Bazel Diff, a system that identifies exactly which Bazel targets are impacted between two commits. Bazel Diff works by treating the build graph like a Merkle tree. Each node in the graph has a hash, and that represents its content and its dependencies. When something changes, that hash changes, and that change propagates upward through the graph. By comparing the graphs before and after a commit, Bazel Diff can precisely determine which targets were affected, and there's no guesswork in this. This is just all math. So essentially, you're creating a cryptographic diff of your build graph, and instead of assuming what changed, you're proving it. So let's take a look at what happened after we rolled Bazel Diff out at Tinder. Once we integrated Bazel Diff into our existing CI workflow without changing anything else, the results were dramatic. In our 90th percentile cases where most builds occur, we saw an average of a 40% reduction in CI compute time. In worst case, with the really heavy build and test everything approach scenarios, the savings jumped to 76%. To put that in perspective at Tinder's scale, that means we're saving about 4 years of compute time every single year at the 40% mark, and roughly 17 years annually at a 76% savings mark. Think about that. We're reclaiming nearly 2 decades of machine time every year just of being smarter about what we test, not about how we test it. These gains came entirely from target selection, no other infrastructure changes, no dynamic orchestration yet. So those numbers were impressive, and honestly, they were well beyond what we expected when we deployed the tool. But when we didn't anticipate, what turned out to be even more meaningful was the cultural effects that happened to the team. Because when you change the build experience that much, you don't just make CI faster, you change how the engineers think about it. And suddenly CI wasn't something to endure, it was something to trust. We started to see shifts in mindset, in ownership, even in how teams started understanding their own code, structure, and impact. And like any big change, it came with a mix of curiosity, skepticism, and eventually a cultural transformation. And let's talk about what that looked like inside the iOS team. So unsurprisingly, there were some cultural impacts after rolling this out. And at first, we saw skepticism. People thought that CI must be broken or disabled because it was just too fast. And when your test suite finishes in minutes instead of nearly an hour, that disbelief is natural. Over time, the skepticism evolved into trust. Developers began to see that the system wasn't cutting corners, it was just working smarter. We also saw a change in visibility. Before, flaky tests were everywhere. We saw that as a shared burden of the team. Now only the teams that own those tests see those failures. And so that changed the ownership model of that and how we diagnose and treat those kind of issues. Another big shift was awareness. People started connecting CI to performance and the structure of our dependency graph. People can now understand that the fast builds aren't magic. They're a reflection of clean modularization and thoughtful change management. And to be honest, this is quite a novel thing, right? Most software in the world has been, the vast majority of all software in the world has been written without target selection. It's like a rounding error in the world of software, right? So we have to respect this as a novel thing. There's only probably 2 build systems in the world that expose primitives required to do this kind of computation. And so that needs to be respected, that this is a new thing. And finally, fast is never fast enough, right? Even with these releases and performance wins, we still have caught back up to having throughput challenges yet again, even with this. So you always have to find that next opportunity to help the team. Well, with that, so at this point, Bazel Diff has had massive performance wins for us, but I think at this next phase, we're going to talk about how we're going to put target selection as the head of our entire CI stack with dynamic orchestration. And for that part, I'm going to hand it off to Connor. So, yeah.
Thank you.
Yep.
Testing. All right, hello, thank you. All right, so Bazel Diff didn't just make our builds faster, it gave us a repeatable framework for identifying where the next gains could come from, the hidden inefficiencies or what we call the dark matter of our build system. With this new visibility, we can clearly see where the pain lives. Slow test targets, overly coupled modules, flaky test ownership. Bazel Diff doesn't just report which targets changed, it surfaces opportunities for improvement. And that's where this gets really interesting. The same mechanism that lets us decide which tests to run can also help us decide whether or not to run them at all. We're starting to view Bazel Diff as the front door to our entire CI funnel, the decision maker of what jobs to dispatch or whether a commit can short circuit entire parts of CI safely. Oh, sorry. As we continue to scale, we realize that even performance wins from Bazel Diff alone were not a permanent solution. The reality is that as your code base grows and as your build volume increases, as developer activity accelerates, you eventually absorb those initial performance gains. Tinder's iOS code base didn't slow down, it grew. More engineers, more features, more integration points. And while Bazel Diff gave us precision, we needed a smarter way to coordinate all that precision at scale. At the time, remote build execution, or RBE, wasn't in the cards for us, either financially or architecturally at Tinder. We couldn't simply scale out by throwing more hardware at this problem. So instead, we focused on improving how work was scheduled and orchestrated inside CI itself. That question led us to the next evolution of Bazel Diff, integrating it deeply as a scheduler at the very front of our CI process through a new internal system we called Arbiter. Arbiter took Bazel Diff's target selection output and used it to drive everything downstream, from build prioritization to test orchestration to artifact routing. In other words, Bazel Diff graduated from being a helper tool to being the entry point to our entire CI. And the shift wasn't just about speed, it was also about flexibility. As our CI responsibilities expanded, things like code coverage enforcement, vendor integrations, post-build analysis, and more, we needed a platform with strong architectural primitives and target selection built in. With Arbiter, compute avoidance became a first-class primitive. CI wasn't guessing anymore. It was reasoning with our change sets. Arbiter allowed us to extend the principles of Bazel Diff to any kind of job. Oh, sorry, just a second. Where's the, I see.
Yeah, just keep, yeah.
Perfect, okay, sorry about that. It allowed us to extend the principles of Bazel Diff to any kind of job, not just build and test. It really gave us a way to reason about omission just as carefully as we do execution itself. So that foundation, which is a flexible orchestration layer built around compute avoidance, positioned us perfectly for the next step, connecting it to a CI system capable of generating and running dynamic pipelines in real time. So this is where Buildkite's dynamic pipelines product came into play for us. It gave us the missing half of what our Arbiter system needed. Arbiter could decide what to do, but it needed a way to express that decision dynamically, to literally like reshape the CI pipeline on the fly. And that's what Buildkite made possible. So instead of a static YAML that always runs the same jobs, we now had the ability to generate a pipeline definition at runtime driven entirely by Arbiter's understanding of the change. So that means that every single commit, pull request, branch could each have its own tailored pipeline that executes only what is required for that change set. So the result was a true dynamic compute avoidance system, one where Bazel Diff identifies the impact, Arbiter decides the scheduling strategy, and Buildkite materializes this pipeline to match it. And what's powerful about this approach is that it bridges precision with automation. So Bazel Diff provides the intelligence of the target selection itself. Arbiter takes that input and provides the control, and ultimately dispatches to Buildkite, who then provides the flexibility to define our pipelines at runtime. So together they create a CI system that's not just faster, but it's continuously self-optimizing. And for the first time, our build system could adapt to the shape of the change and not just respond to it. So at this point, Arbiter was sitting right at the front of our CI funnel, using Bazel Diff to understand the change, and Buildkite to shape the pipeline dynamically around it. We had effectively created a CI system that thinks before it acts. But how much of a difference does that really make once you've integrated target selection? Let's take a look at what we actually saw when we layered in Buildkite's dynamic pipelines on top of Arbiter. So when we brought everything together, Bazel Diff, Arbiter, Buildkite dynamic pipelines, we reached a new ceiling in performance. Our maximum CI time savings jumped from 76% with Bazel Diff alone, which was already quite significant, to a massive 93% once we added dynamic pipeline orchestration. So to put that in perspective, like this improvement alone is just additional years of CI compute time saved annually, all without changing a single step in the developer workflow. And what's remarkable is that the cultural impact of this exact change was actually much smaller than introducing Bazel Diff itself. With Bazel Diff, developers noticed a massive shift. CI felt completely different to them. With Arbiter and dynamic pipelines, it looks the same, but it gets faster and more efficient under the hood. That's a key insight for anyone who's considering using something like Bazel Diff or target selection more broadly, is that once you've integrated these solutions, adopting something like dynamic pipelines for your CI is really like a frictionless, no-brainer next step. So it's a logical next layer that really amplifies that investment into Bazel Diff without really changing anything else about the developer workflow. And from a systems perspective, that's exactly the kind of stuff that we love. Invisible improvement, but there are measurable results here. So with Arbiter and dynamic pipelines, we reached a new level of efficiency. But as with every system improvement, that's not the end of the story. And Max alluded to this earlier. Every time we've increased our CI performance, our developer throughput has grown right alongside it. So that means that our expectations have to keep moving as well. So let's take a step back and talk about where we are now and where we're heading next. So where are we now? We've gone from static CI to something dynamic, intelligent, and adaptive, and that shift has been critical for keeping up with throughput demands of our developers. Every time we improve performance, our developers immediately fill that space with more productivity, more features, more builds. And that's a great problem to have. It means our system is doing its job. It also means that we can't ever stop iterating and making it better. The integration of Bazel Diff and the evolution of its usage through Arbiter opened our eyes to things that were completely hidden from view before. These tools didn't just make our builds faster, but they made the build system much more observable. They exposed inefficiencies, hotspots, and patterns we couldn't have identified with our intuition alone. But once we started seeing CI data through this lens, we realized how much opportunity was still on the table. One thing we learned is that performance gains are temporary, as I just mentioned. You squeeze one bottleneck over here, and the next one immediately makes itself known. For example, even after all these speedups, our developers started raising concerns about our merge queue performance. So we investigated, and what we found was fascinating. So across hundreds of thousands of builds annually, we discovered that test targets almost never fail in merge queue. The real source of friction isn't the tests themselves, it's literally just compilation conflicts. So what can we do with that? With that insight, we took another step further with Arbiter, this time to ingest Bazel Diff target distance metrics, which is a feature contributed by Alex Tarak from the open source community, who we had the pleasure of meeting yesterday in person. Using those distance metrics, Arbiter can now entirely skip execution of test targets whose dependencies are too far removed from the change. So the result for us, nearly 2,000 additional hours of CI time saved every single year. So that's 81 days of compute reclaimed annually at our current scale, essentially for free. And that's really the theme of this entire journey, is just continuous discovery through visibility and observability gained through tools like Bazel Diff, target selection. Bazel Diff and Arbiter didn't just change our CI, it literally changed how we see it, how we measure it, how we shape it moving forward. So thank you so much for listening to this talk. We're happy to open this up to any questions you might have.
Good job. You did great. You did great. You did great. Yeah.
Hello.
For those of us that didn't understand, why is it?
Okay, there it is. For those of us that didn't understand, why in your project you need Bazel Diff, where for a lot of us when we run Bazel test multiple times, the second time we run it, it takes 0 seconds because of Bazel's built-in test avoidance. You may have explained that, but I think there's some of us where it just didn't register.
Yeah, absolutely. Max, do you want
Yeah, so if you have a very performant cache, right? So yeah, I think you have to think of Bazel Diff more of like we alluded to with target selection being a novel technology, right? So most builds are just build and test everything, right? And then investment in companies can be lower than maybe some other larger companies where like, oh, RBE is an option, or these things are an option. A lot of these companies are fetching from a very tiny cache with it's very hammered, right? So you want to reduce that as much as possible. You don't want to have all this egress going into this cache as possible. If you can put that into a tool that runs in 5-6 seconds versus doing a ton of cache downloading or doing a bunch of analysis on those targets they're not impacted, it's just a nice on-ramp to just avoid that. If again, it's the tool kind of, if you have that RBE need, yes, you want to use the warmth of the workers to satisfy that. But I think this tool, it avoids that. It gives you kind of an intermediary point before you get there for very low cost. So yeah.
Certainly. I might also add that other languages or repos might have better luck with their cacheability, or the cache hit rates might be higher, and so that doing much more universal kind of query sets is feasible. For us, we find that there's so much invalidation and noise, especially around our monolithic application target itself, that having something like Bazel Diff at least doesn't allow us to just use the cache so much as a crutch. Knowing that, like Max alluded to, if we hammer it too much, it's certainly going to be a performance bottleneck again for us. So having kind of a compute layer that's much faster ahead of it seems to improve, at least in our case. Yeah. Awesome.
Hey, I was curious, how does Bazel Diff work if there are changes to the Bazel module file? And we use overlays pretty heavily, and I was wondering if it could intelligently only run a subset of.
Yes. So we are now we are finishing our Bazel mod migration right now. As we finish that, we will need to tackle this problem. Is Bazel mod supported? Obviously, I think we're overdoing work right now, but we will have that support, and we will try to figure that out as we get on to that.
Awesome. Thank you.
So, first question I have is, sorry, do you guys use queries or C queries for building the graph? Because I suppose you guys are building 2 graphs and diffing them, right?
Yeah, we support both modes. We have a C query mode and a normal mode, and again, the performance hit of CQuery, as many know, it's high.
Right.
But some builds need that. There's not really a lot we can do in that scenario with that. If you don't need CQuery, you're in a very good place with the performance profile.
For your merge queue, do you guys use CQuery?
We do not need CQuery in our build. No, we do not need CQuery to do our
So
build.
additional interesting question. So I'm not sure people know, but when you do Bazel query, you can actually run into cycles. You can just have a cycle in your graph before it's configured. Do you guys handle that somehow, or
We have other checks prior, so we do have some static analysis that even runs in our build of just some queries and runs we do that are just this is not allowed and stuff. Those are caught in those other checks.
how about I know rules go has a cycle.
Yeah.
So I was
we
wondering.
don't use that
Okay.
a lot.
Okay, sure.
We only have one go. Yeah. So yeah, it's another.
And it's
we literally have one go target.
And you guys
for something.
deploy it as a service, it's deployed as a service, and essentially you talk to that service and.
We would recommend, so if you were to ask me, is we all run it locally, again, because we've kind of alluded to, we've had to, like, we've kind of gone the way of just being really, really intelligent about what we do with compute because we don't have the resourcing for a lot of compute options. So if I were, though, to say if you had more compute, yes, build a service, build a microservice. Do not recalculate hashes. Do not recalculate. Because also rebuilds, right? I think that's another thing. People just go and click rebuild in Buildkite, and it's like, just go to the, just fetch them, right?
Yeah.
Don't redo Bazel Diff. That doesn't make sense. So.
Cool. Awesome. Thank you.
Yeah.
Thank you.
Hi, great presentation and tool. Thanks for making that open sourced. If you're trying to get buy-in in your organization, a lot of the detractors will say, what about like dependencies or transitive dependencies? Are you gonna catch those? And they're worried that maybe if they upgrade a package, that's not gonna be reflected in Bazel Diff. What would you say to those people?
Well, I mean, I think we have all the flags necessary to catch these. You know, we have fine-grained repos where you can say this repo, like go deep inside of it and then try to do an analysis between it. So that's, a lot of companies have gone around that way. You know, if I'm in Bazel Diff, this is a novel thing, right? This is something we're talking about. A very small amount of software has been written using this technology in the world, and so I do think you have to come at it in a humble way and say, go get analysis first. Is there a way you can shadow and say, hey, here's the targets I would have predicted. Have I ever been wrong? And the reality of with a lot of tests, I think we've realized is that most of the tests are never going to fail. Like most of the tests are like, in a lot of scenarios will not fail. So if you come into target selection with that knowledge beforehand of like, these are the targets that usually fail. I've not been wrong for 6 months. That's a great conversation to have versus let's just do target selection and there is a potential of something happening, right? So, yeah.
Great, thanks.
First of all, thanks for Bazel Diff. It's a great tool. Use it at work. I've written about it. It's awesome.
Thank you. Thank you.
So you said you don't use cQuery in your setup.
Yeah.
How do you handle changes to tool chains and things like that not only affect the entire universe if you don't use cQuery?
So again, I think Connor alluded it to. I mean, we're really we have Swift, Go, Java. We don't have a lot of tool chain churn ever really. That's caught in some we could do seed file pass or something where you can say like this BZL file or these Starlark files are like just rebuild everything. It's so rare. It's just our use case. I would say though, if you have those kind of deeper changes, you have to use cQuery. I mean, there's no.
The other thing is, has it come up where like changes to Bazel RC files and things like that don't show up properly?
We put those in our seed file pass. So seed file pass, those reset the seed of all targets. So
you just have like
it's full. It's like a
primordial
full
set of
clear.
files that affect everything.
That'll read that file. That becomes a seed key, and like obviously the calculation of that. So.
Makes sense. Thank you.
Yeah.
Thanks again, Connor and Maxwell.
Thank you.